Hi everyone, in this video I'm going to be going over the Charles Law notes. So Charles Law, it relates volume and temperature. This is probably one of the more difficult concepts to understand in terms of the gas laws. So in this gas law, the pressure is remaining the same. So typically with this, you can have the volume is of course not fixed. So the volume can change, okay? Usually this can be seen in something like a piston that is movable or like a balloon, for example. So when you increase the temperature, the volume will also increase, okay, in order to keep the pressure the same. So let me start here with figure 1. So figure 1, we have a relatively kind of like normal lowish temperature, and we can see that this is our volume here. However, when we increase the temperature, you're going to notice that now the volume increased as well. And that is in order to maintain the same pressure. If we want these molecules to continue to hit the sides of the container at the same rate that they're doing right now, if we're going to make them move faster, then they're going to need more space to move around in order to keep the pressure the same. So to explain that here, if pressure is kept constant, that means the gas particles are continuing to hit the sides of the container at the same rate. We also assume there's no gas escaping or entering the container. If the temperature increases, meaning the speed of the molecule is going to increase, this means the volume, not the side of the container, the size of the container, that's what this should say, would increase. In order for the pressure, the rate at which the molecules are hitting the sides of the container, to stay the same. So in order for this pressure to stay the same, so these both have the same pressure. In order for this pressure to stay the same, if you're increasing the temperature, you need to give these particles more room to move around. If the temperature decreases, this means the volume would decrease. In order for the pressure to stay the same. So one way to look at this, let me go back to that FET here to demonstrate that idea. All right, so again, we're going to be manipulating the temperature and the volume with the pressure staying the same. So let me add some gas particles, and then I'm going to keep the pressure the same. Okay, so look at the pressure. It's 5.8, okay, because that's relying on how often those particles are hitting the sides of the container. If I were to increase the heat, the temperature, now these molecules are moving faster. If I want that pressure to stay the same, then the volume of the container is going to have to increase. Similar to like how a movable piston may be or a balloon works. For example, if you leave a balloon outside in the cold, it's going to get smaller in size, okay? And that's because the pressure, the atmospheric pressure, isn't changing. So if I'm decreasing the speed of the molecules or moving slower, oops, gives you a limit there. If I want that to stay the same, hold on, let me go back this way. So if I'm decreasing the temperature, the molecules are moving slower. If I want to maintain the same pressure, then the size of the container is going to have to get smaller. So that is Charles' law. When the pressure and temperature, when the pressure stays the same and we're seeing changes in the temperature and the volume. So this is a direct relationship because as the volume increases, or as the temperature increases, the volume increases. And as the temperature decreases, the volume decreases. So this is a directly proportional relationship represented by this on the graph and this formula. So again, with these types of problems, you have to first identify what is your V1, T1, V2, T2. So a sample of gas has a volume of, so this is my V1, 752 milliliters, and then my T1 is 25 degrees Celsius. Again, if you ever have degrees Celsius, immediately change it into Kelvin by adding 273.15. So this would be 298.15 Kelvin. And then the question is asking what would be the V2 in liters, that's what we're looking for, if the T2, the new temperature, is now 100 degrees Celsius. Again, immediately convert into Kelvin, okay? All right, now what's important is that right now this volume is in milliliters, but for the final answer for volume, we want it in liters. So I'm going to go ahead and convert this before I even plug into my equation. So I'd have to move 1, 2, 3 decimal places to the left. This is 0.752 liters. So I always like to do that first before I even plug into the equation. So I have my V1, 0.752 liters, divided by my T1 equals my V2, that's what we're solving for, divided by my T2. All right, so again, these are both in Kelvin, which will end up canceling out. My volume is in liters, and that's what I want in my final answer in. So to solve for x, I have to cross multiply. So I would have 298.15x equals, and then we have to do the 373.15 times 0.752, oopsie, 373.15 times 0.752. So 280.6088. All right, to get x by itself, we're going to divide each side by this. Again, you can include the units in your work here, like while you're working through the problem. Like for example, this would have been in Kelvin, this would have been Kelvin and liters, which ultimately would have canceled. Kelvin would have canceled, and we would have just been left with liters. You can always do that. You could just write the numbers as well. And I'm going to take this divided by 298.15, 0.94, we're going to go 4 sig figs, 12 liters would be my final answer. So again, the important thing is paying attention to your units and making sure you're identifying each variable properly. So let's do another one. A sample of nitrogen gas is in a container in a piston that moves freely. So at 0 degrees Celsius, the volume is 375 milliliters. So right there, my V1 is 375 milliliters. My T1 is 0 degrees Celsius, which plus 273.15, 273.15 Kelvin. Easy math there. To what temperature, so that's what we're going to be solving for. So we're going to be solving for T2. We do need our final answer for this. We're going to get it into degrees Celsius, and I'll get to that in a second. My V2 is 500 milliliters. Now this time, because both of my volumes are in milliliters, you don't have to change either of those because ultimately they would cancel out. Because those are in milliliters, those are in milliliters, they would cancel out. However, you still have to always convert your temperature into Kelvin. So I'm going to cross multiply. I plugged in my V1 over my T1. This is in Kelvin. This is in milliliters. This is in milliliters. And then we'll solve for X. So we're going to cross multiply. So 375 milliliters times our X is equal to, so 273.15 times 500. 136,575, and again, this is milliliters in Kelvin right now. I'm going to divide each side by that 375 milliliters. So milliliters will cancel. So right now for my answer, because you always, whenever you're using these equations, you always have to plug in Kelvin into the equation for temperature. So right now this answer, 0.2, excuse me, is in Kelvin. If I wanted to get this into degrees Celsius, I would have to subtract 273.15. So 91.05 degrees Celsius. So if you're ever solving for temperature in one of these problems, your temperature automatically will be in, your answer in temperature will automatically be in Kelvin, and then you can easily convert it back into degrees Celsius by subtracting 273.15.